the next breakthrough, and this is the opening event in the framework of VinFuture Sci-Tech Week, VinFuture Prize Award Ceremony 2025. One more time, welcome and thank you so much for your esteemed presence. Thank you. Distinguished guests, ladies and gentlemen, the Inspirational Talks today is a place where the leading scientists and experts share their perspectives on technological trends that will shape our world in the coming decades through compelling presentations and visually immersive demonstrations. The topics we'll explore in today's talks are essentials for advancing global scientific progress and have profound implications for human lives. Vietnam is deeply committed to supporting scientific development and is playing an increasingly influential role on the world stage. And this Inspirational Talks, the next breakthrough event, celebrates pioneering innovations that have potential to reshape the future of the human health, mobility, and sustainable development. And from advanced robotic hand systems that support movement recovery in stroke patients to the development of artificial hearts that aid in the treatment for patients, and new progress in soft robotics that opening possibilities in manufacturing and human-machine interactions also. Ladies and gentlemen, innovations in agricultural technology and sustainable farming also highlight how digital tools, data-driven agriculture, and scalable green solutions can enhance the food security and contribute to a more resilient future also. Ladies and gentlemen, to come to our program today, it is our honor and privilege to welcome our distinguished guests. It's our honor to welcome Professor Sir Richard Henry Friend from University of Cambridge, United Kingdom, the chair of the VinFuture Prize Council. Welcome, sir. Thank you so much for coming with us for the 5th time. And it is also our honor and privilege to have Dr. Lê Thái Hà, Managing Director of VinFuture Foundation. Thank you so much for being with us today. And it is also our honor and privilege to have the distinguished members of the Prize Council and Pre-Screening Committee. And we would like to welcome the representatives from the sectors of science, technology, and government also. And one more time, welcome all of you come here with us in such a special occasion of VinFuture Prize Award ceremony. Thank you. Ladies and gentlemen, and now could you please direct your attention to the main screen, and let's take a moment to the introduction video clip and also get acquainted with our distinguished speakers through a brief video. So video, please.
The world is witnessing an unprecedented acceleration in science and technology, where each new discovery unveils possibilities that humanity once only imagined. From medicine and robotics to artificial intelligence and smart agriculture, pioneering innovations are steadily shaping the landscape of a new technological era. To share these groundbreaking values with the global community and inspire a vision of a more sustainable future, the VinFuture Foundation proudly presents Inspirational Talks, the next breakthrough. At the event, distinguished scientists will directly introduce their groundbreaking research and applications across 4 cutting-edge areas defining the future of science and technology: robotics and physical intelligence, regenerative medicine and soft artificial organs, neurorehabilitation technologies and assistive robotics, and digital agriculture empowered by artificial intelligence. Inspirational Talks, the next breakthrough, reflects the VinFuture Foundation's vision to honor and amplify scientific research, inventions, and technological innovations that hold the potential to address humanity's shared global challenges. The event brings together pioneering scientists who are directly shaping the future of robotics, artificial intelligence, and human-centered technologies, including Associate Professor Thanh Nho Do, University of the New South Wales, Australia, Director of the UNSW Medical Robotics Lab. He specializes in soft robotics and artificial organs, and is the recipient of the Young Tall Poppy Science Award 2024 and the Google Research Award. Professor Ho-Young Kim from Seoul National University, Republic of Korea, is a leading global expert in fluid mechanics and soft materials. He received his PhD from the Massachusetts Institute of Technology, MIT, and is a fellow of the American Physical Society, APS. He has been honored with the Seoul National University President's Excellent Research Award, along with numerous other prestigious distinctions in the fields of mechanics and engineering. Mr. Dung Do Nguyen, CEO of Infarm, Vietnam, with an AI-powered digital agriculture platform integrating soil sensors, real-time data, and intelligent assistance, recognized among the top 50 AI projects at the Paris Peace Forum 2025. Professor Raymond Kai-Yu Tong from the Chinese University of Hong Kong in China, a pioneering scientist in rehabilitation technologies that help restore mobility for patients. He is a recipient of the Grand Prix of the International Exhibition of Inventions of Geneva and the Global Aging Influencers Award 2021. Being held for the first time, Inspirational Talks. The next breakthrough opens the VinFuture Science and Technology Week 2025, marking the beginning of a journey to bring scientific breakthroughs closer to life and to shape a sustainable future for the shared prosperity of all humankind.
Yes, could you please give a warm round of applause for that incredible journey? And you have just witnessed the glimpse of remarkable ideals and minds that will accompany us through today's program. And to begin the journey of inspiration, let us explore a perspective that takes its cues directly from nature, where observation and imagination come together to reveal new ways of complex challenges. To discover the vision and the pioneering work behind the first story of inspiration, we now invite you to enjoy the introduction video about our opening speaker. Video, please.
In the era of digital technology and automation, robots are expected to play a critical role across highly specialized industries. Yet most robots today are still built with rigid structures and controlled by silicon-based microelectronics, which limits their ability to interact naturally and safely with humans. According to the World Robotics Report 2024 by the International Federation of Robotics, collaborative robots, in cobots, account for only about 10% of all industrial robots installed, and in most cases they still operate in separation rather than working seamlessly alongside people. Inspired by nature, where ants form living bridges, fungal hyphae navigate towards stomata on a leaf, and white blood cells identify and encapsulate invading agents, Professor Ho-Young Kim pursues a radically new direction in robotics, physical intelligence. Instead of relying on processing chips or algorithms, he explores how a robot's materiality and morphology can themselves perform sensing, computation, and response, enabling intelligent behavior to emerge from the physical interaction between robot and environment. His work in soft robots and artificial biological robots, capable of self-adaptation, energy-efficient operation, and agile response, opens up the potential to rethink how matter can think, how intelligence can be awakened through the laws of nature, thus unlocking a sustainable, flexible, and high-potential future for robotics. Professor Ho-Young Kim serves in the Department of Mechanical Engineering at Seoul National University. He is a member of the American Physical Society and a recipient of the Seoul National University President's Research Excellence Award, among other prestigious distinctions in mechanics and engineering. His body of work helps define a sustainable new trajectory for robotics, one in which intelligence is embedded in the robot's physical structure itself, rather than confined to a control chip. The remarkable capabilities and extraordinary adaptability of soft robotic systems, developed on the foundation of self-organizing physical intelligence, will be presented by Professor Ho-Young Kim at today's event. Please welcome Professor Ho-Young Kim.
Thank you. I am honored to be invited to VinFuture Sci-Tech Week. Today, I'd like to introduce to you a novel idea for the next generation robotics, a so-called emergent physical intelligence inspired by nature. When I was a child, my house had a rattan tree in our backyard, making a shade over the rest area. I spent many hours marveling at how they could tangle with each other and grew and shaped themselves as they were, as you can see in the back of myself here. Also, I was puzzled at ants making a long line to carry a food without a master supervisor. And these small wonders of nature deepened my curiosity and interest in science, and eventually I became an engineer working on nature-inspired technology. Today's robots are packed full of sensors, actuators, wires, batteries, complicated software. They are powerful, but also they consume a lot of energy, needs a lot of materials, and are not very cost-effective. In contrast, nature has come up with very ingenious ways to make complex patterns intelligently without complexity. For example, birds can flock in the air, making a beautiful self-organized patterns without traffic signal. Ants can make bridges without master architect. Roots can find nutrients without maps. How can this kind of physically intelligent, simple structures possible in nature, although human-made machines are not be able to this kind of feat? There have been remarkable advances in modern robotics technology, including humanoids and four-legged robots. But still, there are a lot of problems to be solved for these robots to be used in our houses near us, or to take care of the elderly, or to be used in disaster areas, or to be used inside our bodies. In particular, if you're talking about a group of the robots that can accomplish a certain function together, then the cost that you have to invent for the individual robots will be huge with the conventional robotics. So the question naturally arises, how can you make a simple robot which can achieve complex tasks, as nature has done? There are a lot of natural creatures which can accomplish complex functions through physical intelligence in a simple way. One of the representative animals for those natural creatures would be ants. Ants can migrate from one leaf to another by making bridges, okay? And they can also make floating rafts on the lakes, on the rivers, to prevent from drowning on the heavy rainfall. And these ant groups are made as ants are holding on to their immediate neighbors' bodies and actively changing their postures, distances, and orientations. And these ant groups are able to carry out functions that individual ants cannot do alone. And this kind of collective behavior is called emergence. And now, the question becomes more clear. How can you make physically emergent behavior using artificial machines just by tweaking the local interactions between individual agents, instead of relying on the central command to make the whole collective motion of the robot group? And this kind of quest has eventually led me to invent something we call link bots. So imagine a self-propelled particle about the size of your thumb, which has slanted legs, and this can be driven by the vibration. Alone, their motion is not very impressive. They just move around randomly without any special purpose. But what if they are connected by links, as you can see here, which have notches where the individual bus can be inserted, and if they are connected to make a particle chain like this, and then when they are set into motion, something interesting happens. They begin to move in a direction with a special purpose. And this is the blow-up version of the self-propelling particle that I used for the LinkBot. So the actual LinkBot that I showed in the movie is 3 times smaller than this, the sample. And this is the link that I used to constrain the relative motions of the self-propelling particles. And this is a notch angle. And the degree of the notch opening defines how well you can move in response to other agents' motion. So if you have a very small notch angle, then their relative motions are constrained. But if you have a large notch angle, their relative motions are rather free, and you can have a large degree of freedom of these LinkBots. So individual self-propelling particle acts like individual ants. But if you link these particles together, and they behave like a group of ants, capable of intelligent behavior. And just by tweaking the link angle, then you can accomplish a lot of contrasting functions. For example, when this LinkBot encounters a gap in the wall, some LinkBots with a large notch angle will just obstruct the gap. But if you just change their notch angle, then they are able to penetrate into the gap and transverse the gap. Or a certain design of the LinkBot just maintains the direction when they encounter the broken walls. But if you just tweak their notch angle a little bit, then this LinkBot can change direction smoothly and go into the interior area of the broken walls. Also, through a very narrow channels, some LinkBots can pass through this channel very fast, but other designs of LinkBots will be very slow in going through this channel. And also, some LinkBots tend to leave this curved surface early, and other designs of LinkBots are very good at following the curvature of the surface. And the third one here is really expert in following the surface curvature. And they can make almost a U-turn here. So in this way, using this roundabout structure, you can sort different kinds of LinkBots. And let me talk about something useful. So when there is a movable cargo, then this design of LinkBot just carries this cargo forward. But if you change the LinkBot design a little bit, then this LinkBot will wrap around the cargo, and then it brings it backward. And sometimes this LinkBot can just bypass the obstacles, depending on the notch angle. And also, there may be a LinkBot which just wraps around the cargo and just going nowhere. And actually, I'm already talking with a company based in Korea, which is specializing in cleaning ocean pollutants. So imagine that this cargo is the plastic waste on the lakes or the rivers, on the ocean. And if you have a fleet of the LinkBots from the shore, then you deploy them. And then those LinkBots will enclose those plastic waste on water. And then they will squeeze them and then bring it back to the shore by this physically emergent behavior. You don't have to control each boat's trajectory at all. In the multi-component environments, these LinkBots are able to multiple functions. So they go through narrow corridor and then enclose the cargo and then bring it back. 2 LinkBots of different design. The first one goes around the circle and pushes the cargo. And the second one has a sort of the vagabond. So they just move around very freely without interacting with the obstacles very deeply. Also, two link buds can either compete or cooperate in response to the external surroundings. So for example, two identical link buds pushing the dumbbell, their forces are cancelled out and they cannot go nowhere. But if a two link bud design meeting the dumbbell, and one is pushing the dumbbell and the other is pulling the dumbbell, so that the dumbbell speed is much higher than when it's carried by a single link bud. And when they meet the gap, a single link bud cannot pass through this gap when the wall is curved. Whether it starts from the left or right, it cannot pass through the gap. But they can cooperate, and then they can go into the gap. All right? So as a quick summary of the first part of my talk, I have shown you that it's possible to emulate the collective behavior of ants using self-propelled particles and very simple link structure. You don't need to pre-program each individual agent's motion. It's just the physical intelligence that guides you to have this kind of rich dynamics of the collectives. And let me turn to a different perspective of physical intelligence that you can find in nature at the level of a single organism, not the group behavior. Especially, we are interested in plants because plants have come up with very ingenious ways to come up with the solutions to cope with the ever-changing environments because they don't have muscles, so they cannot move freely as animals. Especially, today I'd like to introduce to you a curious behavior of tip-growing cell. So for those kind of plant cells, the growth is extremely localized at the tip. So the growth only occurs at a very small portion of the tip, so the motion is directed. Here, I'm showing you a pollen tube, male pollen tube, chasing the female ovule. So this is what happens in the pollination process in flowers, okay? And this pollen tube is chasing the female ovule by the chemical cue released by this female ovule, okay? And can you emulate this kind of directed motion of the cell using robotics technology or modern material science? Actually, in addition to the pollen tubes, the germ tubes of some rust fungi are also able to grow at the tip. And those rust fungi tend to infect the plant leaves by invading into stomata. Stomata are breathing holes of the leaf, and some plant leaves are covered with the ridges, and those stomata are distributed along the ridges. And to maximize the possibility of encountering the stomata, these germ tubes tend to grow perpendicular to the surface ridges, as you can see here. Okay? In this way, you can find the stomata, and then you can invade into the hole. And it was proven that even on the natural leaves, on the artificial leaves, these germ tubes can grow perpendicular to the surface pattern. And how can this kind of intelligent behavior emerge? There is no brain in the cell. There is no central command. Just a physical interaction between the cell and the surface structure of the leaf orients the growth direction of this cell. So this is physical intelligence. Then how can you emulate this kind of physical intelligence with a modern mechanical technology? So we came up with a novel material system which grows like a cell. Here, we inject a solution which has a special characteristics that it rapidly solidifies when it's in contact with the water. Therefore, this rapidly solidifies at the stem, side wall, but the front tip remains liquid. or soft, so that the growth is only possible at the tip while the side wall is surrounded by the solid wall. In this way, you can emulate the tip growing behavior of a liquid cell. And also, in plant cell, the material distribution is very similar. In plant cell, the side wall is surrounded by rigid cell wall, and only the tip of the cell remains liquidish or soft, so that growth occurs here. And if you compare the tip growing behavior and the growth from the base, then you will see how important it is for the robot to grow from the tip to steer into the forest of the pillars. When this system from the tip, it can freely navigate into the obstacles. However, when the growth is from the base, when it encounters the obstacle, it easily buckles and coils. Okay? So if you want to make a robot which can freely navigate into your obstacles or some unexplored area, you have to come up with a material system that can grow from the tip. And I'm already talking to a global semiconductor manufacturer based in Korea to clean up the pipes in semiconductor manufacturing fab. So it's their headache that the pipes of the semiconductor fab is frequently clogged with the chemicals. And to clean up the pipes, they have some kind of robot that can go into the clogs and then release the chemical inside. Okay? So we are talking about making a new robot based on this kind of tip growth behavior of the plant cell to invade into the clogs of the pipe and release the chemical and then clean up the pipe. And as I mentioned before, this tip growing cell is able to grow perpendicular to the surface ridges, and this is indeed what you observed using the artificial tip growing system and the artificially made surface ridges. There is no command. Okay? There is no pre-program. We just let this system in contact with some surface structure, and physical intelligence guides the growth of this robot. So why do we care about this simple physical intelligence of nature for next generation robotics? In fact, there are many applications where complicated humanoids or four-legged robots are not needed. Okay? Imagine a group of small robots that surround the tumors or infected area in our body. And they do the treatment, and also they can actively change their configurations in response to changing conditions of your human body. In that case, the functions that you can see from the ends will be more useful than the complicated structures of the humanoids. Also, you can think about a growing robot that can penetrate into the collapsed buildings or the earthquakes. Okay? You don't need a fancy humanoids for the rescue functions in this kind of disaster area. What you need is a very long cylinder which can go penetrate into the damaged area. In this kind of scenario, needs physical intelligence from the tip-growing cell, not the humanoids. So in summary, I have shown you that nature has come up with very ingenious ways to manifest physical intelligence, as you can see from the ants at the group level and from the plant cells in the individual organism. And also, we can come up with an artificial system that can emulate this kind of physical intelligence through link bots or tip-growing material system. And these simple robotic systems consumes less energy, consumes less synthetic materials, cost-effective, and eco-friendly. So therefore, they can solve a lot of problems that modern conventional robotic technology cannot do. So I'd like to invite you to my journey to find more solutions from the nature that can be more useful in the years to come where humanoids and other high technology cannot still solve for our humankind's wellness. So with this, I'd like to conclude my talk, and thank you very much for your attention.
Thank you very much, Professor Ho-Young Kim. Incredible, and I think that your presentation reminds us a lot about our childhood when the nature sent the signals for Earth, by the way, but did we only see it? We have to notice it, and we take action and make a change like the way Professor Ho-Young Kim did, and really serves our life with his research product. And now may I assist you to open the Q&A session for all the audience right here to deliver the questions to our Professor Ho-Young Kim. So could you please raise your hands, and our staff will assist you with the microphone over to deliver the questions. Yes, I can see a lot of hands is raising. Yes, please, the man in the front, number 2. Yes, please.
Hello. Thank you very much. One question. First of all, really impressive and interesting result. My question about the link bots. If there's no P-program for each of the element in the link bots, how does it know to move left or right, or the direction to move? The link.
Can you say it again?
Yes. So the link bots, yeah. If there's no central control or there's no pre-program for each of the element in the link bots, how does it know to move, like what the direction to move? For example, how does it know to move left or right?
Oh, okay, yeah, yeah, okay, yeah, yeah. Actually, that link bot has a V shape, so it's not symmetrical overall. So so there is a center bot which can direct the direction of the whole link bot. So it's a V-shaped. So there's a center and side links. So in this way, you can predict that this bot will move in a fashion that resembles the sharp V shape, okay? And the notch angle controls how this V shape can breathe, open and close, okay? And depending on the notch angle, the breathing degree of this V changes. And when this V can be spread out very much, then it can block the wall. And if this V is very sharp, then it can penetrate into the gap. So in this way, you can find out which direction is the front and which direction is the rear. And after that, whether it's going to go to the left or to the right, we don't know. It's kind of random. But what we know that is that when this V interacts with some obstacle, then we can find out, we can predict whether it can go around or whether it can penetrate, okay? But the exact direction from left or right, we do not have precise control over it.
So let's say if we don't have the precise control of the link bot, let's say if I have a problem that I would like to control it in the right direction, follow a right path, do you think that that would be possible?
Oh yeah, so actually, as I mentioned, there's a center bot and the side bots. And if you give a little bit of control on the center bot, then this center bot can guide the whole, particle chain. So if you want to have that control, then I can have a little bit of, steering function and the center bot. And the other side bots will follow the motion of the center bot. So in that way, you can solve that problem.
Yeah, thank you very much.
Thank you so much, Professor Ho-Young Kim, and thank you, the audience. And I think that we only have one more room for the last questions for our professor about this inspirational talk. And just please, the man in black right behind the first questions.
All right.
Yes, please.
Okay. Do you need power or electricity for the link bot?
Actually, anything needs power. So you have to vibrate it. So, either the vibration energy can be supplied from the environment, or it can be self-vibrate. So for that self-vibration, you need a battery and this kind of thing. But if you can supply the vibration energy from the surroundings, then the individual body itself does not need the power.
And one more question, please. What is most important benefits of physical robots compared to the modern robot, like in terms of low energy or?
Yes, yes, exactly. You don't need central control, so you don't need huge computational power. So you don't have to invest much energy. Also, since you don't need much control or the software or hardware, the material design can be very simple.
Simple?
Yes. So it's a simple, meaning that it's cost effective, and you use less energy and less material, so it's eco-friendly and also cost effective.
All right, thank you very much.
Thank you so much, everyone in the audience, and thank you very much for your answer, very detailed, that help us understand the research product with the promising energy saving, low cost, and less dependent on the technology and wider applicability. Thank you so much one more time, Professor Ho Young Kim, and ladies and gentlemen, please give it up for our special guest, the opening guest. Thank you so much, and could you please turn back to your seat so we will follow the next part of our inspirational talks today. Ladies and gentlemen, as we all know that we all carry a natural heart within us. The quiet engine sustains our lives. But have you ever imagined that an artificial heart can mimic the softness, the rhythm, and the functional sophistication as a real one? And yes, please direct your attention to the stage as we explore this groundbreaking frontier with our next speaker, a leading researcher from University of New South Wales, Australia, who will introduce us to a fascinating world of soft artificial heart. Video, please.
Cardiovascular diseases pose one of the greatest threats to human health. According to the World Health Organization, WHO, in 2022, approximately 19.8 million people died from cardiovascular diseases, accounting for roughly 32% of all global deaths. However, every heart is unique, differing in morphology, myocardial fiber kinetics, and tissue mechanical properties. And generic models struggle to fully replicate the underlying pathophysiology. Although interventional technologies have made great strides, surgical planning still relies primarily on static imaging or simulations, data that do not reflect the heart's mechanical motion under physiological conditions, thus creating an information gap when making critical decisions and forcing clinicians to act under high-risk uncertainty. The soft, beating artificial heart, developed by Associate Professor Thanh Nho Do, offers a breakthrough beyond these limitations. Made from highly elastic soft materials, the model can simultaneously reproduce the heart's motion, pressure, and blood flow, just like a real human heart. By enabling patient-specific customization, it allows surgeons to test, rehearse, and assess potential risks before entering the operating room. From its early development, Associate Professor Thanh Nho Do's work has gained international recognition and is considered one of the pioneering directions in next-generation biomedical robotics. Associate Professor Thanh Nho Do is a senior sciential lecturer at the University of New South Wales and director of the UNSW Medical Robotics Laboratory. His research focuses on soft robotics and artificial organs, and his contributions have been internationally recognized, including the Young Tall Poppy Award 2024, the Google Research Award, and his inclusion by Reuters among the top 4 robots of the year 2023. At today's event, Associate Professor Thanh Nho Do will introduce new frontiers in cardiovascular medicine, where soft robotic technology and physiological simulation are combined to recreate the living rhythm of the human heart in his keynote address, Artificial Heart. Please welcome Associate Professor Thanh Nho Do.
And thank you very much for your time to be here today with me. And good morning, everyone. And today, I would like to share with you about one of my research that I think it will shape the future of the cardiac care in the next decade. I would like to share with you one thing. this is the most beautiful and complex organ structure that we have known so far. And its anatomy actually is different in each one of us. And the difference in individual becomes significant when a disease occurs inside the heart. And the question that I may ask all of you here today, can we renovate the human heart outside the living body? The human circulatory system actually a non-stop recycling loop powered by the heart. It has to bring blood with carbon dioxide back to the lungs for gas exchange, and then we can bring blood with rich oxygen, go back to bodies to fuel the living cells and provide nutrients. And you can see here, the beautiful organs, actually they can beat about 60 to 100 beats per minute. And it seems that a normal person like us can live for 70 or 80 years. Our heart can beat about 2.5 to 3 billion times, which is remarkable. And with a normal activity like walking like this, the heart can pump blood about 5 to 6 liters of blood per minute. And if we consider that a normal person can live for 70 to 80 years, our heart can pump about 200 millions of liters of blood, and enough to fill over 80 on the size of swimming pool. But unfortunately, not everyone here or people in the landmass have the healthy circulatory system. And that's reason why we have the cardiovascular disease. Cardiovascular disease normally happens inside the blood vessel. For example, stroke happens when blood from the heart supplied to the brains is blocked because of thrombosis, blood loss, or even the aneurysm. It can lead to the rupture of the vessel. And it will lead to the death of the brain cell. And inside the heart, in order to maintain the blood from moving in the right direction, we have a tiny doors, which is the heart valve. And if the heart valve they have a disease, the blood cannot move in the right direction. For example, they can leak backward from the left ventricle to the left atrium, and this will impair the pumping function of the heart. Heart attack. Actually, the working mechanism similar to stroke, but not only happen at the heart surface. When the artery outside the heart actually be blocked by thrombosis, it can lead to the death of the cardiac muscle. And this is actually the sudden events. It happened very quick. And when a large areas of the heart muscle they dies, our heart cannot pump, they stop, and people will die. And both heart valve disease and heart attack can lead to the heart failures. This is the chronic condition where the heart have the inability to pump sufficient blood into the body. And currently, heart failure actually the final stage of cardiovascular disease. And many people developing the heart failures. And the best way to treat the heart failure is the heart transplant. And we also have many other types of cardiovascular disease. But how do we treat the cardiovascular disease? Before I show you the treatment methods, I would like to share a recent statistics that I take by this year, 2025. You can see here, currently 20.5 million people worldwide die because of cardiovascular disease. And it occupies 33% of all global deaths. And cardiovascular disease deaths actually much higher than cancer and any other disease combined. By 2050, the numbers of people have cardiovascular disease will increase to around 729.5 million people, which is about 110% increase from this year, 2025. And most of cardiovascular disease normally happen and occur in low and mid-income countries like Asia. And sadly, they occupy about 58% on desk globally. How about our beautiful country, Vietnam? We have amazing people, smart children, great scientists, but still have the same trends. About 261,000 people died because of cardiovascular disease, and occupy 33% of all deaths combined. Unfortunately, Vietnamese people currently living with heart failures. Around 300,000 to 1.6 Vietnamese people are living with heart failures, and this number will increase significantly in the next decade. And the best way to treat the cardiovascular disease, actually we have to use medical devices. Here, cardiac device. It can be stents to open the blockage inside the arteries, or even the mechanical pump that can help to augment the pumping function of the failing heart. Or we can use robotic heart valve to replace the faulty one. But as you know, no cardiac devices are safe and effective to be used inside the patient's bodies, because after implanted, they have many complications that we cannot predict in advance. For example, the mitral regurgitation, actually the heart valve disease happens when the mitral valves between the left ventricle and the left atrium, they cannot close properly, and blood will leak backward from the left ventricle to the left atrium. And the best way to treat the mitral regurgitation, we have to perform the repairs or the replacement of the defect mitral valve. About 50% of all the patients with this disease, they are not suitable for the open surgeries because of complication risk. And advance in robotic technology allow us to use a flexible medical tool, here transcatheter mitral valve intervention, that they inserted this tool to the left vessel of the left, and then they reach the left atrium. There, they can perform the valve repairs or replacement. But as you know, about 40% of the patients, after they have the replacement of the mitral valves, they develop the complication. It means after we place the new mitral valve here, they block a blood from the left ventricle to the aorta. And currently, it's very challenging to predict. First of all, in clinical setting, medical doctor, they will take the image of the heart, and then they use the clinical result of 1.7 centimeters square to determine whether the patient is eligible for the mitral valve intervention or not. However, around 34.2% of the patients, after determined by the clinician that are eligible, they develop the obstruction. And for those who don't satisfy this area, they don't develop the obstruction. And this can lead to about 60.8% of all patients are excluded from the transcatheter mitral valve intervention. And the question I want to raise today is, how can we actually predict the complication risk, and we can select a suitable patient for the mitral valve intervention? Heart failures are also affecting many people around the world. Currently, 64 million people affected by the heart failures. And 50% of the patients related to the heart failure with a reduced ejection fraction. What does it mean? It means the human heart, they cannot contract completely or not strong enough to pump blood into the body. And the best way to treat this type of heart failure is heart transplant. And for the patient who waiting for heart transplant, they have to use cardiac devices such as the heart pump. Actually, this one, the LVAD heart matrix, that's currently being used to extend the lives of the patient who have the heart failures. And this one we implanted into the apex of the left heart, and they pump blood from the left ventricle to the aorta, this device. Unfortunately, After the patient being implanted the LVAS, 43% of the patient, they develop the right ventricular failures. It means instead we use the LVAS to support the left ventricle. Now after we implanted the LVAS, we induce the right ventricular failures. The reason is that the left and the right ventricle, they share the common septum. Implanted LVAS will affect the position of this septum. It can lead to impair the pumping function of the right ventricle. And if both ventricles going to be failed, the patient only survive 23% after 2 years. And currently, no effective methods can determine whether the patient is eligible for the LVAD or not. And the second question I want to ask you today, how can we early identify the complication risk for the patient who require the use of LVADs, and then we can avoid many complications? And the absence of a reliable literature tool have forced the clinician into a very challenging decision. Either we just postpone the treatment for ineligible patients until their disease gets worse, or we just go ahead with eligible patients despite we don't know any complication. It can lead to the fatal outcome. And today I would like to share with you the solution that we can address the question. Can we rebuild the patient's health outside the bodies? And we use this innovative tool to select a suitable patient to early identify the complication risk before we actually placing the cardiac device inside the body. The human heart actually very beautiful, but very complex. They have the cardiac muscle surrounding the left and right ventricle in a very complicated way. And advance in medical imaging can help us to capture a very detail of cardiac muscle and the heart structure outside the bodies. And if we can use the patient medical imaging data, we can reconstruct the heart outside the body. And let's imagine that I take the picture of the patient's heart and then use medical imaging data to reconstruct the heart outside the bodies. And in the lab, we use different medical imaging techniques like MRI, CT scan, ultrasound, to reconstruct the heart in the 3D computational model. And then we utilize the advanced manufacturing techniques and our artificial muscle to rearrange the 3 muscle layers of the heart. And you can see here, using this method and advanced software technology, we're not only able to rearrange the heart complex motion, but also we can rearrange the complex heart disease like the heart failures or even the heart valve disease. And now I would like to show you the simplified prototype of our artificial heart that we built in the lab. And this is the simplified model of the soft artificial heart that we built in the lab. And this device that consists of the left ventricle, the left atrium, and the aorta. The geometry of the components actually we constructed from the high-resolution medical imaging of the patient. And by combining with the soft robotic technology, we could rearrange the complex motion of the heart, including the helical twisting, compression, and so the shortening from the apex to the base. And if we can control this artificial heart, we could rearrange different types of heart disease for example, the heart failures with the reserve ejection fraction, or even we can rearrange the complex hemodynamics for medical device testing. And the possibility of this technology can help us to advance the cardiac research to study the new type of disease. And now I would like to share with you about the application of this sub-robotic heart. Slides, please. And what can we do with this sub-robotic heart? Many cardiac devices are being developed, but the option of reliable tool that can help them to move in the next stage of approval. And that reason why many cardiac devices cannot get the FDA approval. We can use this system to develop the new type of surgical tool, or even we can use this device to rewrite the complex heart disease for research of our study, or even we can use this technology to help the surgeon to train the complex surgical procedure, such as transcatheter mitral valve intervention, or even we can use this technology to predict how well the cardiac devices will work inside the patient's body before we actually implanted them. And we begin to explore one of the most challenging heart failures in the world, heart failure with the reserve ejection fraction. What does this mean? Instead of the heart normally contract and relax to fill with blood, and this disease, they prevent the heart from fully expand to fill blood and pump into the body. And currently, around over 50% of heart failure cases belong to this disease. And this disease, they are associated with multiple cause factors, hypertension, diabetes, that are very challenging to replicate by any animal models or cardiac devices. And because of this lack, no cardiac devices available for the treatment of HFpEF. And in the lab, we try to react one of the first sub-robotic hearts that can rearrange this disease. For heart failure with the reserve ejection fraction, the pressure inside the left ventricle increases significantly, and for a long time, it will damage the mitral valve. And then the blood will leak backward from left ventricle to the left atrium, and the pressure inside the left atrium also increases as well. And in order to rearrange this type of heart disease, we apply the closed loop control algorithm that allows the left ventricle to adjust their reaction force to the filling pressure. In other words, we can control the compliance level of the heart that match with the patient data. And you can see here, we use the LVAD heart matrix, one of the latest technology to demonstrate that we can use the FDA approval device to treat this disease. We connected the LVAD heart matrix to the left atrium and then to the aorta. And as you can see here, when we increase the LVAD pumping speed, the pressure inside the left atrium significantly decreases. This means we can treat the heart failure with the reserve ejection fraction. And we are also using this technology to eradicate the heart valve disease. For example, the mitral regurgitation is actually one of the most complicated heart valve disease, and it's very challenging to treat. And in combination with advanced manufacturing technology and the 3D motion of the surface of the heart, we can recreate different levels of the mitral regurgitation. You can see here, by adjusting the tension of the pavilion muscle inside the surface of the heart, we can control different disease levels. And then the medical doctor or researcher can use this platform to develop the new robotic heart valves and allow them to check whether the heart valve is safe to be used before they can implant it inside the patient's body. In addition to that, we also use the platform to develop a new type of surgical tool. For example, we created a flexible robotic catheter with the in-situ force sensor. And we use actually this technology to test the function of the device that can help us to measure the interaction force between the heart wall and also the tool for safer operation. And we can use advanced technology to perform some cardiac ablation that can treat some certain of heart valve disease, for example. And what is the main driving goal for my research and the future developments of this disruptive heart technology? As a bio-robotic researcher working in biomedical engineering field, I do believe that we can do much more better for the patient. For example, heart failure currently affecting 64 million of people worldwide. And this number will significantly increase in the next decade. And the best way to treat the heart failure is the heart transplant. But as you know, per year, we only have 4,000 donor hearts available. And 64 million of people waiting for donor hearts. Only 4,000 available. It means the demand is much greater than the supply. And people living with heart failure, they have to be on a very long waiting list. And many people die. And currently, left ventricle assisted device, or the LVAD I saw there, can be used to extend the lives of the heart failure patient who are waiting for heart transplant. And globally, only 42,000 of LVAD heartmetry, the latest technology from Assoc, have been used in a patient with heart failure. How about in Vietnam? We have only one case performed at one of our hospitals this year. What does it mean? LVAS is not designed for everybody because they have many complication risks. After being implanted the LVAS, patient develop the complication, right lung infection, even the right ventricle failure. Or even after the patient, they receive the normal heart, they have to use the anti-rejection therapy, or sometimes they require to replace the new one. And my remit, in the short term, within 5 to 10 years, for example, I would like to advance this robotic technology to achieve the smarter, a better solution that can help to support the clinician to select suitable patient for cardiac devices. And for the long term, I would like to develop a total artificial heart that can be implanted inside the patient's body. I do hope that this technology won't have any infection or complication. But this vision cannot achieve by me alone. It needs the collaboration research by the multidisciplinary team. And I think experts in robotics, AI, medicine, material science can work together. I strongly believe that this mission is possible. By combining advanced tissue engineering and emerging sub-robotic technology, we can create the total artificial heart that can help the patient extend their lives. And all together, we can save the future of cardiac care with a sub-robotic heart. Thank you very much for your time.
Thank you so much, Associate Professor Do Thanh Nho, with your inspiring presentation. Thank you so much. And your invention opens the door for the health sector in general, and especially for cardiovascular diseases in all over the world, especially in Vietnam. And now, may I help you to open the Q&A sessions for all the audience here to deliver the questions to our Associate Professor Do Thanh Nho. And yes, I could see the hands waving right here. Yes, please. Yes, the man in black, like in the 5th row. Yes, please. Thank you.
Thank you for the presentation. I love that experience. My question is, like we all know that the rapid increase of the cardiovascular disease case, right? So what about the cost and also the efficiency of your project? About the cost and the efficiency compared to that, the price that the patient needs to pay for that, because we all know that the number of the patient is increased rapidly right now, right in that at the moment.
Yeah, regarding the cost, actually, you can see in the picture I saw, to be honest, the cost of the device is very cheap. Because we use up the cell material like silicon elastomer, 3D printing technology to make the shape of the heart. But at the time, I do believe that advanced in medical imaging can help us to quickly capture the patient heart image and then quickly reconstruct in the 3D computer models. And then we use this medical imaging data and advanced manufacturing, we can quickly rearrange the patient heart outside the bodies. And currently, we don't know exactly how long it takes to do that. And that's why we have to work together. Medical imaging experts like Professor Mindo there, robotic technology like Professor Ho Yong Kim and Raymond, or even material people can work together to advance this technology. But currently, we use this device to test the LVAS before we can recommend the LVAS into the patient. And we start collaborating with some medical doctor in Sydney.
Yeah. Thank you so much.
Thank you,
And
yes.
I got another question for you.
Yes, please.
Sorry.
Yes, please.
Yeah. So I see that you have like the real test like on the patient. Yeah. So do you, any difficulty, and do you have any idea to solve the difficulty during the experiment?
Yeah, the most challenge for working with the patient is we have to collect the data, and sometimes the medical imaging techniques not widely available. Sometimes we have the poor medical imaging data that we cannot reconstruct the patient heart outside the body. And the second challenge is for each patient, they have different heart anatomy. And sometimes we challenging to capture exactly the hemodynamics of the patient, even the 3D motion. I do think that with the further advance in the field, where the patient data are widely available and with a good quality, we can further validate the technology and we can bring to the clinical clinic. Thank you. Yeah.
Thank you so much.
Thank you so much, the audience, and thank you so much for your questions. I'm so sorry that the time is limited, so could you please, if you have any questions, please write it down with the paper in front of you that we prepared, and we can hand it to the professors so that we can answer it later. Thank you so much for your questions and your concern with the presentation about the invention from Associate Professor Do Thanh Nho. Thank you so much.
Thank you very much.
Thank you. Distinguished guests, ladies and gentlemen, as we continue with our program today, let us turn to a story about restoring one of the most fundamental expressions of human connections, the simple ability to move the hand. Yes, for many people, these seemingly effortless gestures can become an immense challenge, yet it remains a symbol of independence, dignity, and hope. And behind every breakthrough that helps someone regain this ability is a long journey of compassion, creativity, and scientific dedication. It is a journey that blends engineering with empathy and innovation with a deep understanding of human needs, and to discover the visionary work that is turning these challenges to new possibility for countless individuals. So could you please direct your attention to the main screen for the video clip?
Population accelerates in aging, a major healthcare imperative emerges: stroke and neurological disorders. According to the World Health Organization, WHO, more than 3 billion people worldwide are living with neurological conditions, now the leading cause of disability. Each year, nearly 12 million individuals experience a first-ever stroke, and over 7 million lives are lost to this disease. Despite significant advances in modern medicine, neurorehabilitation and motor function recovery remain formidable challenges, compelling the scientific community to explore new trajectories beyond the boundaries of traditional therapy. This imperative is precisely what motivated Professor Raymond Caillou Tong and his research team to develop Hand of Hope, a robotic exoskeleton capable of sensing neuromuscular signals and interpreting a patient's intent to move. This exoskeleton supports motor rehabilitation and neuro retraining for stroke survivors. The device has now been deployed in over 20 countries, and it has paved the way for ExoMuscle, a next-generation, bio-inspired, soft artificial muscle system that is wearable, powerful yet compliant, introducing a human-centric dimension into rehabilitation therapy. Professor Raymond Caillou Tong holds a PhD in biomedical engineering from the University of Strathclyde, UK. He is founding head of the first department of biomedical engineering in Hong Kong and is ranked among the world's top 2% most highly cited scientists in biomedical engineering and rehabilitation engineering, according to the Stanford University Citation Ranking. He is currently at the Chinese University of Hong Kong, CUHK, where he leads research in flexible biomedical robotics, neurofeedback activation, and accelerated functional recovery systems. Professor Raymond Caillou Tong's innovations have marked a new milestone in rehabilitation medicine, where technology empowers people to regain mobility and independence in daily life. His breakthroughs have earned him numerous prestigious international honors, including the Grand Prix of the International Exhibition of Inventions of Geneva and the Global Aging Influencers Award 2021. At today's event, Professor Tong will present breakthrough biomedical robotic solutions that transcend the constraints of conventional rehabilitation methods, restoring hope, movement, and independence for stroke survivors in his keynote speech, Rewiring Hope, Engineering Human Potential Through Soft Robotics. Please join us in welcoming Professor Raymond Caillou Tong.
Thank you so much for the invitations. I'm Raymond Tong from the Chinese University of Hong Kong. It's my first time to Hanoi. It's a very beautiful city. But today my job is to see my journey, how to bring hopes to our patients. So you can see there's a lot of stroke patients around the world. It's more than 100 millions. Maybe 1 out of 4 actually have stroke in their lifetime. But you can see this lady, he's smiling. He's a stroke survivor. You know, how to bring happiness to them. I think this is part of our job as an engineer, as a scientist, but how to do it. Before seeing us, actually, she's one of them. After stroke, no matter you're rich or poor, actually, half the brain may be damaged. Then what they can do? He may paralyze, so they cannot move their limbs. Maybe some of the daily tasks, very simple, they cannot do. And what's happening? They may need someone to help them. But when I was young, you know, I visited one of the elder centers. I saw a lady. And then we provide all this service to her. She's happy. But a moment, she cried, you know, in front of me. Says, Raymond, you're young. You're, you know, scientist. Can you do something? Can you do some things to regain my life? You know, I want to be independent. But one thing It's my doctor, physicians, and then therapists. They say, I have stroke more than 2 years. Nothing can be do. My hand will be like this. Can you do something for us? So at that time, I think about, I'm doing the neuroscience, I'm doing the robotic, just like some of you. Can I do something for her, for the community? Then I start my journey 20 years ago. Then I start to learn a lot of different things. As an engineer, I start to learn about the brain, the neuroscience. Then we find out after stroke, the pink area, you can see, the damaged cells, you cannot regain the functions. We also do the animal test, for the stroke rat. We make the rat stroke, yes, but we learn how to recover. Then we find out the damaged tissues, you cannot regain any functions. But amazing thing is, how much percent of the brain we are using today? For all of you, maybe just around 10%. What's the remaining 90%? Are they useless? No. Actually, they are the reservoir. In case anything happens, they can use those reservoir tissues to relearn some of the functions. So now, we notice there's an opportunity. Can we reroute those neural network and regain some of the functions to them? First things, we need to learn from the MRI, EEG, how the brain regain the functions. The other thing is, after they think about what to do, how to learn it, actually, we find out is you need to give them some feedback, real time. So if I think about moving the hands, then actually the hand need to move. Then I know I'm doing the right things. The tissue is very interesting. From our research, we find some tissues is actually used for leg movement, but after training, they can use it for the hand. So the brain is very neuroplastic. So what we need to do, not just make robot to help the patients to move the hand or walk. We want to train, actually, their brain. So we developed journeys to detect the brain signals, maybe from the EEG or from the muscles, and then directly control the robotic in the real time. So we conduct a very interesting study. Nowadays, you can see a lot of humanoids or exoskeletons. The people wear it, they can walk around. But after you take off the exoskeleton, can they walk by themselves? Most of the answer is no. The brain didn't learn anything. So we do one more thing. The robot move when your brain is thinking about the movement. So we have this, what we call the intention-driven robot. So what's happening is, when the patient thinks, I want to move my wrist, the robot will move. If the patient didn't think deeply, the robot will not move. Actually, during the training, you ask the patients, are you feel tired after training about the hand? The answer is no. I feel tired, my brain. I need to focus. I need to learn. I need to learn how to use my hand again. So in this randomized control trial, the patients, both groups is very happy. One group is just a robot to move the hands and then the wrist for them. The other group is they need to think and then the robot will move. After that, we look at the data. The brain only learn properly is with the intention-driven. With the passive group, you just move it. Maybe it's less spasticity. The range of motion a bit better, but the brain didn't learn anything. They cannot generate a lot of motions by themselves. But the intention-driven, totally different. Then we notice the elbow, the wrist can move. But then next challenge in our journey is, come back to the lady. The lady says, my hand cannot move. All the doctor, everyone tell me, I cannot do it, anything. I can regain my functions. Then we visit again. We think about, the hand is the most difficult one. No one's tell us 15 years ago, the hand can regenerate the functions after stroke, after 6 months. Okay? But then we think about, there's opportunity. We link to the brain, we make the first robotic hand in the world. But then when you look at the hands, how many finger joints we have? 14 of it. We need 14 motor. It's impossible. It's very heavy. You cannot grab a lot of objects, So we invent the hand of hope. And then the 5 motors, we can move all the fingers to do these actions. Then we use the brainwave with this hand and hope. We start our journey to regain the functions for the stroke patients. After that, definitely our journey is not finished because the patient is happy about the hands. Then the next question comes, how about my leg? I want to walk. Okay, so they are a bit greedy, but it's fine. And then we build the ankle robots, we build different programs. So actually now we are not just doing the research. Actually, we become a service. So our journey is continuous because we are not achieve, our ultimate goal is every body part can be recovered after stroke. So we build a hand taster using a brainwave, do more dedicated functions. We also build the exo brace. Now, this time, it's not just for the stroke patients, even for the small kids, because the robot nowadays, we are not just using the motor. We can use what we call the soft material, soft robotic. So the latest advancements in our lab is building the artificial muscles. So today, I will have some demonstrations to all of you. And then, so as to see how powerful we can regenerate our functions using those artificial muscles. In our lab, we are very proud to be here in the VinFuture because I'm traveling around the world because the technology is not just limited in the Hong Kong. You can see in Hong Kong, we are giving to the patients in the hospital, in the rehab center, also in their home. And then in the right lower corner, you can see this is a young lady. She got stroke 1.5 years old after the heart surgery. It's very young. But using our robotic hands, at the age of 4, actually she can regain some of the function nowadays. So you can see we can build different size. We can build different technology, personalized for her and then for the whole family. Now you can see after the 15 years of journey of the hand of hope, the people notice hand can recover from our research. A lot of robotics coming out, particularly for the hands. So it's good, everyone can do it, but the function is not good enough. You can see some of them can grab a bottle of water, but in our lab, we can do more. The hand is so robust. With the soft materials, we can grab all this fine movement. So the patients before stroke, they can do maybe writing with their dominant hands. Now they can do it again. Rather than to learn with the non-dominant, I think it's very hard for us to write our name at the end. So those functions with the brain together, we can recover the brains better. Then we build a lot of devices, very portable nowadays. We have the EMG amplifiers. We can use the muscle intentions to do it. Definitely, we have the BCI. Nowadays, because of the yellow mask, and then everyone know about the BCI, but actually we start our journeys 10 years ago. And then we find out brain control the hands directly. That's very effective. So this is our latest research paper in one of the top journals. We find out is before, in the 15 years ago, if we do any training after stroke for 6 months, only 10% of the patients have significant improvement in their functions. But now in our lab, we can generate 80% of them have a significant improvement. So for us, it's happy because it's sometimes the engineer with the clinicians, we can change the clinical practice nowadays. But we didn't certify it because the patients work hard for the hand, for the ankle. But those big joints, like the shoulders and the hip, very difficult. And one of the challenges we faced 10 years ago is how to train the hands, like the wrist, to do this supination, pronations, all these functions. It's very complicated. Our hands very delicate. I built the robots before, 10 years ago, it's around 5 kilograms to just move the forearm, like pronation, supination. It's too heavy. It's very difficult to use. But when we look at the muscles, how they move the outer bone and the radial bone to do this pronation, supination, it's very genius. They just use the muscle contractions. So we think about, we build the muscles again. So in our lab, we build this 100 grams artificial muscles using the air pressures. Now we can lift up 20 kilograms, this water bucket. So we learn from the human muscles. So we contract the muscles is like the fiber, one by one. So with the technology of the soft material, it's very tough, and then we can use a small pressure. Actually, we can contract those soft material and then pull all this fiber one by one, and then actually we can generate a large force. And we can 3D print those material nowadays, and then we can also have machines to wire those artificial muscles, and then it's very flexible. So later in my talk, and then I have demonstrations, how powerful is this exo muscles. So let's look at this video. This is my dream, how to move the wrist to do the actions, just like human muscles. So flexion, extensions, easy to be done. But the next one, pronation, supinations. You can see we can do it easily nowadays. So we can do with just 4 muscle groups together. This is a real patient's stroke. He have stroke 5 years ago. You can see that his hands, the wrist, nothing can be done. But then we start this training with the robotic hands, with these artificial muscles. So we give him the most difficult task. Pick the objects, turn, and lift it up. Those are complex actions, using the brainwave and the muscles to do it together. After 20 sessions of training, take off the robot. You can see he can pour the water. Even one of his favorite tasks is doing what? The right-hand corner. Can you tell me what he's doing? Pick up his phone. Nowadays, the phone is too big, you cannot operate just one hand. You need the other hands to hold it, and then the good hands to just surf around. So he's so happy. So in our lab, a lot of patients coming to train one thing, to use their smartphone. So it's better than the other technology, just feeding them or drinking, I think using the phone is, you can do the things for the whole day. But after that, we found out the potentials there. How about the kids? And then we collaborate with the Australia Cerebral Palsy Alliance and then the University of Sydney. They have a very good organization for the cerebral palsy kids. And then they come to our lab. They see the soft robotic hands, all the things. Then we have one thinking about, how about the kids? You can see this is a cerebral kids in Hong Kong. He's 2 years old. His fathers and our clinicians want him to stand up. Nothing can be done, okay? But now, if we can train the brain again to help this kid to stand up. So you can see in the middle slide, actually we use these artificial muscles, synchronize with the walking and train him to walk. Then after a while, and then what's happening? One day, after 15 sessions, my lab technicians just call me. The boy stand up by himself. I say, impossible. No one can stand up with this boy. But he stand up. Then I rush to the lab, and then I take this video. First time in his life, he can stand up. Then I know there's a potential there. So after he can stand up, he can walk. So actually, it's in our lab, or even in the special school in Hong Kong, actually, there's start implement those. Definitely, also in Australia, we are doing this. So we see there's a big potentials for the soft robotic, and also how to train the brain again. Because before 5 years old, actually, the muscle is still building up, and then if you don't do anything, they will build up this, we call the spasticity. They have this couch gait. And then after that, you just can do the surgery to lengthen the tendons, all the things. And then they may be likely to be wheelchair bound. But now, if he can stand up and walk, maybe change his life. Not just his life, his family. So after that, and then we go back to the hospital to show the surgeons, to the doctor, oh, we can do this. They say, you can do more than this. What? Then we do it back to the adult. And then some even go for the knee surgery, and then they can train the knee again, and then do those crazy sport, okay? And then, so the technologies just go back and forward. So in our research lab, definitely we are good in the rehabilitation robotic, from the mechanical exoskeletons all the way for full body. Now we can also do this artificial muscle for the full body. And also with the AI, actually make the control system more easy to be implemented. So combine both together, actually we can implement those nice technologies together. But for us, I think more important, not just writing the scientific papers. We go to the social media, we go for the exhibitions, we also come to hear the VinFutures because we want more people to know about it. And then the more important is they can use it. So that's why we visit hospital and also we have center. So yesterday I also visited the VinFuture University here, the medical school, and also a few days later I will visit the Hanoi Medical University. So I hope not just to bring the technologies to the audience here, also bring the technologies to Vietnam, to other countries. So I think this is the aim, feedback to the ladies I just mentioned, bring the hopes to them. So when I saw all the patients, they fight so hard to gain independence. They fight so hard to regain their life. As an engineer, we face a lot of hurdle, a lot of difficulty. A lot of clinicians told me, this cannot be done. Nothing we can do. But we believe, together with the patient, we can do it. So with me, there's some of the technology I bring together. First of all, this is the hand of hope. So it's a mechanical design, and then you can see we can adjust the finger length with this design. So one hand can fit for 95% of the human adult hand. And then we just use one motor with the linear system. Actually, we can control the whole upper limb. And when we design this, actually, we just observe. Actually, when we bend the fingers, it's very interesting. In the biological, actually, they have a synergy when we're bending. So we just use this 65, 55 degree, this rules, but the human hand, actually, we can control smoothly. So actually, we learn from the observation from the human hands. But after that, we built even soft robotic. So with the soft materials, we can, with the air, we can generate all these functions. We can make a very, very small size, as you see in the videos. And then the pump, also we also make it very, very small, like this small pump. We can use it right now. And so after that, this is the exomuscles we built. How do you feel this, the power of this? Maybe I would like to invite, one here. Oh, okay, maybe this young lady. Okay, can you come? And then we give a quick demonstration. Thank you. So can I have a microphone for her? Yes. Thank you. So what's your name?
My name is Chi, and I'm a student of Vin University.
Okay, Chi, thank you. So this one has two muscles. It's for the forearm, for the pronation, supinations. So what I like to try is try one muscle. So you can put down the microphone here. So you just pull this muscle as strong as possible. Yeah. Do you have your breakfast this morning? Okay. Yeah, pull it as hard as possible. Just don't let it to be contract, okay? So I just turn on the pump. Okay. So he's not making up. It's really tough because this can generate 10 kilograms. Okay, so let me try again. So you can pull it. Yeah, you won't break it, you won't generate 20 grams. I will invite some of the strong men, to try, My students like to do that, Okay, not breaking me, breaking the muscle, okay. So it's very fast and strong. But then this strong is very dangerous. Am I right? All this motor is very dangerous. But we also have this safety, just like the water. If you block somewhere, they float the other pathway. So this also will be safe. So I can demonstrate. So I will just, which finger you don't use today? You use all your fingers. Oh, this one, the little fingers. Okay, we put this here. So I pull it, and then you put the fingers in between. Don't scream, okay? Yeah. So we do it. Pull, okay? Are you feel anything?
I'm not feeling any pain.
So actually, using these muscles, we can train them much safer, Thank you, Chi. Thank you for coming up here. Thank you very much. Thank you for our audience. Thank you very much. So welcome any questions, and then or maybe some of the strongest men on the stage or down there, you can come and try it out if you feel that you can have 20 kilograms. You want to try?
Yes, thank you,
Oh,
Professor. So now it's time for the Q&A sessions, and anyone with the questions can deliver to our professor. Yes, please. May I assist you with the microphone? Yes.
Yeah, thank you very much for the inspiring talk. My question is, what is the remaining challenges for your products? How to make it more accessible to everyone? Let's say in the future, after a stroke patient can just buy your product, bring it home, and do the training.
So actually, we also make it become a package, something like that. It's not for promotion, but it's just we need to have some of the staff company, and then we start to deliver to the hospital first, and also go to the rehab center. So we make it more affordable. But I think the key is the clinicians. We need to educate the clinicians, how to change the mindset and how to collaborate with their training together. Because if they can move more, actually the therapy will be changing together, so they can recover much better.
Thank you so much, Professor. So we are available for maybe more questions for our professor. Yes, please. Yes, please.
So thank you very much for your very wonderful presentation. So I just have one very small question that the main purpose of this product is to support the patient, right? So I wonder that do you have any plan to connect your robot arm with the brain thinking or signal from the brain? So for example, it can apply for some people get the accident and they lost their hands and they can support in this case.
Yes. Actually, we have, in my slide, you can see there's a different group of patients. The most larger population in Hong Kong, maybe the stroke, because the elderly and then the cardiovascular, there's a lot of stroke, But we also have some is with the brain injury. We also can do that, no matter it's the adult or the kids, maybe after the cancer, we also have those. And then definitely, we also have a few is with the prosthesis, amputee. Then they can use the brain wave to control the robot hand, That's for the procedure. But for us, we are more interested, to train the brain. So it's those still have the limbs, and then they can regain the function. That's the more fascinating, Yeah, but we have the technology, so that's why we work with those for the prosthesis hands. We do that research.
Thank you so much, Professor. So can I hold it a little bit? So
yeah.
I could feel, wow, this is really lightweight, ladies and gentlemen, and it is so easy for the patient and especially for the families who are taking care of their loved ones. And I think the most importantly is it can reduce the burden for the health systems and the hospitals for the patients. Thank you so much for your presentation, and we hope that this is your presentation proves the spirit that technology for life, like the way VinFuture heading to science for life. One more time, thank you so much, our Professor Raymond Kai Yu Tong, and thank you so much for all your questions. Thank you.
Thank you.
And yes, may I kindly invite you to be back to your seat, so we will come to the final presentation in our inspirational talk, the next breakthrough. Ladies and gentlemen, let us turn to a field that sustains it all, agriculture. Ladies and gentlemen, in a time of climate uncertainty and rising food demands, smart farming is reshaping the way we grow, manage, and protect our crops, creating meaningful impact on farmers, communities, and environment. Behind this transformation are innovators who bring the technology and practical insight together to solve real challenges on the ground, helping agriculture become not only more productive, but more resilient for the future. And with that spirit, we now invite you to discover the story, the mission, and the breakthrough solutions to our final speaker through a following introduction.
Land degradation and desertification are becoming major challenges for the socio-economic development of agricultural nations. According to the United Nations, almost a quarter of the Earth's land area has already been degraded, leading to declining crop yields, volatile food prices, and sharply increased greenhouse gas emissions from soils, further exacerbating climate change. If this trend continues, as many as 95% of global soils could be degraded within the next 30 years. Yet it is precisely the agricultural sector that can become the center of the solution, forging a regenerative and sustainable agriculture for the future. With this vision, Mr. Zhongdo Nguyen, co-founder and chief executive officer of VinFarm, introduces an integrated solution combining soil sensing technology, real-time data, and an AI-powered digital assistant. This system empowers farmers to make data-driven decisions, improving yields, reducing input costs and emissions, and enhancing long-term soil health. His approach represents a fundamental shift in agricultural science, from intuition-based experience to data-driven precision agriculture, where digital technologies, open data, and artificial intelligence work together to create a smarter and more sustainable farming ecosystem. Within just 1 year of its launch, VinFarm has supported farmers across 14 provinces in Vietnam, while expanding internationally to the Philippines and Africa, helping to combat desertification and ensure global food security. Thanks to these achievements, Mr. Zhongdo Nguyen's solution has gained worldwide recognition. Selected among the top 50 AI projects at the Paris Peace Forum 2025, awarded the Market Readiness Prize at the Agri-Food Tech World Championship 2024, and ranked among the top 3 winners of the Qualcomm Vietnam Innovation Challenge 2025. From the farmlands of Vietnam to the global stage, Mr. Zhongdo Nguyen proves that technology and innovation are not here to replace humans, but to work alongside us in building a greener, more sustainable world. Today, he shares how technology can help restore the Earth's vitality and reimagine the future of agriculture through his talk. Empowering farmers with AI for a regenerative future? Please welcome Mr. Zhongdo Nguyen.
Good morning. My name is Zong Nguyen, co-founder and CEO of VinFarm. Now, I am between you and your lunch. So let's talk about how to grow food. Our promise is simple: grow more with less and save the planet. Today, I will tell you how AI can empower farmers to earn more while rebuilding soil health and building a regenerative future. Now, this image has been very familiar to many of Vietnamese this year. This year reminded us that climate change hurts and costly. 400 deaths, 340,000 homes, and 500,000 hectares of cropland flooded. But many big losses begin invisibly. We don't need to wait for a big flood or a fierce drought to kill a crop. Just a small change in weather may already hurt the plants, because farmer depends on experience when it comes to decision making. But when the weather pattern shifts, experience turn into guesswork, and guesswork is very expensive. Let's take a look at fertilizer, a fundamental input for farming. 60% of applied fertilizer unabsorbed by plants globally. And this is a 120 billion US dollars worth of fertilizer wasted every year around the world. It damages our cropland. Around 1/3 of the cropland around the world damages, degraded because of over-fertilization. And this problem even more serious in Vietnam, because we use 2.5 times more fertilizer per hectare of cropland than the world average. Because we are a small country with big populations, therefore we have to make the soil work too hard. And fertilizer also a main source of global greenhouse gas emissions. So why on earth that we put so much fertilizer? The problem is every farm is unique. Different soil, different practice, different weather. But agronomists and fertilizer company have to come up with formula that universal so they can scale, right? So that's a big gap. And the only path into sustainability and prosperity as well for farmers is regenerative agriculture. And really AI opened that door. And this pathway is now even more urgent for us to take than any more before, because as predicted by FAO, the Food and Agriculture Organization of UN, by 2050, we had to produce 70% more food. At the same time, many of countries, including Vietnam, have committed to net zero. So optimizing fertilizer yield is now mandatory. Our team has recognized this. We are soil scientists, agronomists, engineers, who are willing to stand in the mud with farmers. We build in the soil, we innovate in the farmland, and we build trust with the farmer with their crops. So our solution is a blend between IoT and AI, so that we can deliver affordable but large precision soil sensing kits that can provide the farmers with not just data on what the nutrients available in the soil for the crop, but also recommendation for them what to do. So this tool can measure NPK, moisture, pH, temperature, and EC, electrical conductivity of the soil. Let me do a small demo for you to show how it works. So helping me would be Miss Lan Phương from VinFuture University. And she carry a kit that now is the most very popular among farmers because it's very affordable and it's easy to use. So please, let me help with this. Yeah. So this is the kit that we ship to the farmers. It comes with a transponder that can connect to the phone, and it also sensors. So Ms. Lan Phương studied communication, but today she wants to be a farmer. So we just need to connect the sensor to the soil near the root. Now this is cam canh, it's a mandarin orange in Vietnam, very popular among Vietnamese, especially when it's close to New Year Tết. And amazing that we always put that near the canopy because that's where the root is, right? And now she already connect with the device. And she will start doing the measure. So when we connect the transponder with the sensor, the transponder will send the power to the soil sensor and at the same time receive data. So camera, you can help to record this? Yeah. So now it will receive the data from the transponder, start doing the analyzing, and then we will see the result and also some recommendation. So this is actually a cloud-based technology. And we also aware that in many also remote area, there's no phone signal. So in the latest upgrade of the device, that now they can measure without a phone signal and they can see the result when the phone signal available. We also develop a new technology that can measure and give recommendation when without any signal at all. So there's a lot of improvement we have been conducting every day to make this technology available to every farmers in every corner of the country and then every corner of the world. So now you can see that the phone start receiving the data from the transponder. You will just take a few seconds and then you can see the result. Yeah. Okay, so now we have the result. Yeah, so this is the result that we can see It's in Vietnamese, but it tells you on available. So this is the nutrient that is the plant can absorb, right? On nitrogen, potassium, and phosphorus, EC, temperature, moisture. So a bit wet, but it's very little nutrient in the soil, and the pH, which is low but not too bad, right? But when we also can come to AI, when it could tell you what to do with this and how to improve the soil health and the yield for the farmers. We have been this technology, we have been for Vietnamese farmers, and we're soon launching the English version as well. So we can ship it to other countries, and that many farmers around the world can start using this technology. So now the AI is working hard. Now, without this technology today, what the farmer have to do? They have to send the soil test to the lab, and they have to wait for a few days to a few weeks and only receive the raw data. So this is the recommendation, right? And in Vietnamese, it already recognized that very low nutrients, right? So they suggest the type of fertilizer they need to apply for NPK formula 15-15 or 15-20, right? Focus on, especially on potassium and nitrogen, right? And they also suggest on the next step when you should maintain the moisture below the 60%, from 50% to 60%. So a long list of recommendations, and we keep talking to the app. So just to help them to do two things at the same time, which is all in the past impossible. Increase yield, increase income for the farmer, and at the same time can save the earth and cut down on the greenhouse gas emission. Thanks, Ms. Lanfern, so much. So we have tests in the field, and farmers have received remarkable results. Can I have the slide? Like for coffee, we have achieved 30% more higher yield with 30% less fertilizer compared to their conventional practice today. And that can convert into about 70-80% of increase in income for farmers. It's a significant change in their livelihood. It also can bring the better crop quality as well, because for many crops, the fertilizer affects the nutrient in the fruit, and also make sure that the crop are more resilient to the climate change. But we not just focus on individual farms, right? With data, our goal is to lift up the entire value chain of agriculture. We can help, with data, we can help to predict the demand for the agriculture input. We can predict the yield, so that's very important for the output buyers. And then we also connect the data that inform the farmers, inform the government, or provide the traceability of the product in real time, right? So what you can see, those are sensors that come in the central highland of Vietnam when we have the very high density of the farmer using our technology. And next year, we're going to launch the sensorless model, so that farmer can access the precision agriculture with just about $2 per month. And that opened the door for all the farmers in this country and beyond to using a new technology like N-Farm. So how we do this? A conventional sensor out there is provide moisture, temperature, EC, and pH. And most of them cannot detect NPK. And for those who can, usually they will disclaim on their website, on their products, that is not very precise. In N-Farm, we fuse the dynamic sensor data with the physiochemical properties that we collect through the farmer input, through the apps, and also with the weather data as well. So we can localize the measurement at the highest level to achieve the lab precision level. With that, we can predict the soil nutrient, so nitrate, phosphate, potash, and very soon we also can predict the nitrous oxygen, which is very important for us to fighting climate change, because nitrous oxygen captures the heat 300 times more than CO2, carbon dioxide. And at the same time, not just helping the climate, we're also helping the soil, right? So we can inform the farmer and guide them on pH stability, buffering capacity, moisture stress index. So that is really a complete package to help the farmers. Better climate, better soil health, and better income. So we just launched the product last year after 2.5 years in R&D, and farmers welcome our products. We have installed in Vietnam 1,200 sensors, 70% through the digital channels, 90% self-installed by farmer. We just ship the product to them. And that is telling that it's how easy to use this kind of technology. Because when we started, a lot of people say, no, farmers don't know how to use technology, and they likely to decline this. Or they don't care about environment, and that's not true. We also we realize that 80% of farmers are aware of the overuse of chemical in agriculture. Just that they don't have a right tool to change the way they've been farming for many years. And we have put many farmers on TV channel because they come to national television to tell about how we use technology that help improve the crop, the quality, and the quantity, as well helping the farmer in the remote areas. So compared to many other products available around the world, we are just about 10% of the price, a lot easier to use, and very useful. So that we are ready to serve the world of 550 million smallholder farmers, 97% of the farm in the world. I just talked to Mr. Rahul, come from Davis, California, US, and he also a farmer. And he told me that for organic farmer, which is usually have a small farm in US, they need such a tool. And even they practice organic farming, they still need to know the nutrient in the soil. And this tool is still very useful. So hopefully we can go to US very soon. With our effort, we have been recognized globally in our innovation and impact, and been supported by organizations around the world. And we're very honored to be here today to share with you our story at VinFuture Science and Technology Week. Partner with us to build a regenerative future. Thank you for listening.
Thank you so much, Mr. Dũng Do Nguyen, for your impressive presentation with the cam canh tree right here on the live stage. Thank you so much. I'm really impressed with the ideal view that precision should not be a luxury. Precision must be a right, the right for the farmers, and you and Farm are doing everything you can for the food security in the next futures. Thank you so much for your presentation, and now may I help you to open the Q&A sessions for all our audience to deliver the questions. Yes, please, may I invite the man over there? Yes, please. Yes, please.
Thank you so much for your inspired story. And I have one question. So from your perspective, so what is the fundamental shift to for the AI-driven agriculture to move from the pilot project to the truly scalable and national-wide transformations? That's what is the need to make the scalable, scalability.
Thank you for your questions. I think your question is what do we need, right,
yes.
to scale this technology to the national level?
Yes, that's right.
I would say that first, from the user demand, the demand is high, right? And we can see that through our acquired customers. Now, the good thing in Vietnam that all farmers using Facebook, 98%, so very easy to reach the user. And they all share the interest in this. So the big concern for them is always two things. One is affordability, and second is trust, right? Because for farmer, they don't want to be the first to use something that's very new, right? So to overcome that, we have been working closely with government. So we have just last week, for example, we have equipped, agriculture promoter, like promotions officer in Lâm Đồng province, with this device. So those people can come out and measure the soil and advise the farmers, right on spot. So that build the trust, right? Build the trust with the farmer and explain them this is a new technology that can help them, right? We also work doing a lot of training sessions, right? But we understand that the main problem here is it's the very first time that the people have a tool that they can measure the soil nutrient. As one farmer told us that we make the plant to talk, we make the soil to talk. And a lot of information may go against their common sense. And so education is very critical. Like give you one example. Now, a farmer may follow certain formulas, right? Guide by textbook and agronomists say that a certain time of the year you need to apply this formula of fertilizer. But when they measure the level of nutrient are not the same as their fertilizer. And they think, oh, this is made wrong. But they didn't know that now the soil release the fertilizer to the plants. So and of course the soil don't release exact the same amount, right? They may release nitrogen much faster than potassium, right? So a lot of education so that we understand and they trust us. And of course, I have to say that the AI help, the AI chatbot, because at least they can talk to the app and understand that. And my last point is, at the end of the day, we need funding to scale, because right now we're still manufacturing at the smaller size, a small quantum. And to improve the consistency of the product as well as to reduce the price, we need funding so that we can produce at mass scale so that we can sell to farm at much lower price.
Yes. Thank you so much.
Thank you so much for your answer. Yes, may I invite one more questions from the audience for our Mr. Đỗ Dũng Nguyễn. Vâng ạ. Yes, please, the man over there, right next to the previous one. Yes, please. Yes, please. Yeah, Professor.
Thank you so much for your nice and interesting presentation. I want to ask if there's the possibility to extend to other forms of nitrogen in soil, such as organic nitrogen or ammonium. Is it possible, or is that would be too difficult besides nitrate?
Yeah. So I think that now our measure is using machine learning, right? And based on the dynamic soil sensor data as well as physiochemical property of the soil. So we can, based on the measurement of nitrate, and then predict other form of nitrogen's nutrient in the soil as well. We're working on that, like such as nitrous oxidants, right? So we're working on that. Also, the other one is nitrite as well. So we're doing a few forms, and perhaps we can update next year, because the goal, at the end of the goal, is just to expand on the measurement of nitrogen, because it's so critical for both the soil, the crop, and the climate. And then be able to measure the greenhouse gas emission and give the farmer who practices credit, right? Thank you for your question.
Thank you so much. Thank you so much, our audience, for your questions. And one more time, thank you so much for your presentation and your invention. One more time, ladies and gentlemen, please give it up for all of our speakers, and especially the final one. Ladies and gentlemen, and with that inspirational talk, we are coming to an end of our inspirational talk, the next breakthrough. And I would love to express our deepest thanks to all of your presence here, our distinguished guests, ladies and gentlemen. Maybe that we could see each other in this afternoon, and don't forget to follow the Science for Life Symposium and the VinFuture Prize Award ceremony premiered on VTV1 Vietnam National Television on December the 5th, and the dialogue with the 2025 VinFuture Prize laureate session that followed the next day at the Vin University. And each event is an opportunity to deepen the dialogue, spark new collaborations, and celebrate the scientific advances that are shaping better future for humanity. Thank you so much for coming with us today. We love you all. Goodbye for now and see you later. Distinguished guests, ladies and gentlemen, on behalf of the organizing team, I would love to invite all of our distinguished speakers. Could you please turn back to the stage so we can take a photo together to remark this days. Thank you. One more time, I would love to invite all of our distinguished speakers, 4 speakers in our inspirational talks today. Please turn back to your stage so we can take a photo of you to remark this day, the very opening event of the VinFuture Sci-Tech Week. Thank you so much. And I would love to invite Associate Professor Do Thanh Nho. Could you please turn back to your stage? Yes, can you look at the camera? And we are ready to take a photo. 3, 2, 1. One more time. Could you please step forward in the center of the stage? Yes. 3, 2, 1. Thank you. And one more time, I would love to invite all of our distinguished guests, the members of the VinFuture Pre-Screening Committee and the Council to be on the stage for the photo of this event. Yes, Associate Professor Do Thanh Nho. Here are our distinguished speakers of our first event of the VinFuture Sci-Tech Week in the Inspirational Talks. 3, 2, 1. Beautiful. Thank you so much. And one more time, I would love to invite all of our distinguished guests, the member of Pre-Screening Committee and Prize Council of VinFuture Prize to be on the stage right now so we can remark this special moment together. Thank you. I would love to invite, yes, Professor Sir Richard Henry Friend, our distinguished guest from front row. Could you please, yes, to be on the stage? Thank you so much. Could you step aside a little bit on the left? Yes, please. And look at the camera, and we are ready to take a photo. 3, 2, 1, go. Thank you so much one more time, our distinguished guests and our audience. And we will see each other in this afternoon with the dialogue with our distinguished guests. One more time, thank you so much. Goodbye for now, and see you again.